Hello everyone, welcome back to the classes of ECE111. So today we are going to learn about node analysis. So it is a circuit solving technique using which we can go for another way of dealing into circuits. So this node analysis is based on KCL, which we know as Kirchhoff's current law, which states that the algebraic sum of currents meeting at a point is 0. Or in other words, we also can say that the number of current entering a point is equals to the number of current leaving that point. So whenever we are dealing with KCL, we come across the term called node. So what is a node? A node is a meeting point of 3 or more than 3 branches. So suppose let us consider this point where we have 3 branches together and two currents are moving in and one current is moving out. So this generates a node. So in some of the theories you might find that meeting point of more than 2 branches is a node, but as we know with respect to KCL, a node is a point where the current divides. So if you consider this as a node, so we have two currents moving in and one current moving out, but in this case whatever is current moving in is moving out. That means this is a series current. So in this point there is no division of current. So that is why we have we call a node to be a node when it contains 3 branches together. So now moving into node analysis. So in node analysis, suppose we are considering a circuit like this. Let us consider a simple circuit. So suppose we are having a circuit like this. Now we want to determine the or go for node analysis. So first, before going into node analysis, we have to identify how many nodes are here. So as we can see here, we have as per our definition of node analysis. So this is a node where we have 3 branches. This is another node where we have 3 branches, and below also we can see this is also a node which contain more than 3 branches, right? We cannot call this as a node because this point and this point and this points are same. There is no resistance in between, so these 2 points are same, so we can call all this together points as a node, right? So this circuit contains 3 nodes. So for node analysis, first thing is we have to identify the node, then second thing is we have to identify a reference node. So reference node means normally where the voltage used to be 0, that is called as the reference node. So here in this circuit we can consider this as our reference node. Okay, so the remaining nodes are where we have to determine the voltages or voltage drop across the remaining nodes. So for example, we have 2 nodes. So suppose this is number 1 and this is a number 2 node. So we call it as suppose V1 and we call this voltage as V2. Okay, then let us give some resistance names R1, R2, R3, R4 and R5, and this is suppose our voltage source Vs, this is suppose our current source Is. Okay, so as per our KCL definition, so current moving in is equal to current moving out, but in this case whenever we are considering a node analysis, what we consider is the current should always move out. Okay, if we are considering this node, then current is moving, all the currents are moving out of the node. Similarly, if we are considering this node, then also currents are moving outside the node. Okay, so if we are considering this convention, then our equations will remain same. So whenever we are solving it, whatever we are solving, then our equations are going to be same, and our similarly the process of solving the equations will remain the same. So that is why we will follow this convention. Like in case of our mesh analysis, we have considered the current always moves in clockwise direction. So like that, here we are considering the currents in all the currents are moving out of the node. Now suppose if we are getting suppose this is my current I1, this is suppose current I2, then this is suppose current I3. Suppose I am getting the value of current I2 as negative. So that means the current that we have considered should be in the opposite direction. So accordingly we will get the value of the current plus the direction of the current when we finally solve the numerical, right? So now here suppose we have three currents, so I1, I2, I3. So in this case for node at node 1, so what we can write, I1 plus I2 plus I3 equals to 0, right? Because all the currents are moving out, so addition of all the currents should be equals to 0 as per our rule of KCL. So now this I1 can be written as with respect to voltage, right? So if we are go in writing this currents with respect to voltage, then as we know, as per our Ohm's law, so V equals to IR. So the current will be V divided by R, right? So here in place of I, we are going to replace it by voltage divided by the resistance. So what will be in case of I1? This is our I1. So here we have one voltage is V1, second voltage is Vs. So as per our direction, this is moving from high to low. So it will be V1 minus Vs divided by resistance, which is R1. Okay. Then for I2, this is our I2. So we have only one voltage, remaining is 0. So 0 potential. So we can write it like V1 minus 0 divided by R4, or we can directly write it as V1 divided by R4. Okay. Then third one is I3. So for I3 it will be V1 minus V2 divided by R2. Okay, equals to 0. So this is our equation 1. Then for the node V2, so then at node 2, so now we are directly going to write down with respect to this V by R ratio. So if we start here, so first current is moving outward in this direction. So we have V2 minus V1 divided by R2, okay, plus the below one is V2 divided by R5. Now in the third case, we can see here in the below current IS is already mentioned here. So the current that is flowing in this path is IS. So in place of V2 or any determining any relation with respect to voltage by resistance, we can directly put here the value of your current, which is nothing but IS. But the direction of IS and the direction we have considered are opposite in direction, so it will be minus of IS equals to 0. Okay, so now we have two equations, two unknowns, because the voltage and the current source value will be given. So we have two unknowns, V1 and V2, two equations, so we can solve it. Okay, so this is how we go for nodal analysis. So this is the way how we solve nodal analysis. So now let us take an example and see how it can be done. So we are considering this circuit now. Okay, so in this circuit we have one source, two source, three sources, right? And we have four resistances. So in this first one, what we have to do is we have to determine the nodes. So in this case we have one node here and second node is here, and the ground one is your reference node. Okay, right? So let us consider this voltage as V1, this voltage as V2. Okay, so at node 1, if we write down the equation, so it will be V1 minus 60, right, divided by 20, plus, then this current is moving up but our current direction is moving down, so it will be minus 1. Then next one is plus V1 minus V2 divided by 30 equals to 0. This is our first equation. The second equation will be at node 2 we have V2 minus V1 divided by 30 plus V2 minus 40 divided by 50. Okay, then plus last one is your V2 divided by 100, right, equals to 0. So now when we solve this, two equation, two unknown, so we are going to get, so I am directly writing the answer. So we are going to get V1 as 67.2 volt and V2 as 48 volts. So now suppose we are asked to determine the current across this 100 ohm. So what will be the current across this 100 ohm? This current, we already know this current is given by this voltage divided by this resistance. So the current across 100 ohm, suppose I am naming it as IL. So it will be IL equals to V2 divided by 100. So V2 we have got 48. So divided by 100, it will be 0.48 ampere. Okay. So this is as simple as that. So we can determine any circuit or we can solve any circuit using nodal analysis. So now let us quickly consider another example containing a dependent source. Now here, as we can see, it is already mentioned that this is our node, because this cannot be a node because we do not have any resistance here. So the potential drop across this point and this point are same. So we have only one node, and this is our reference node. Okay, so let us write down the equation. So at node 1, okay, so first, okay, let me use another. So we have, this is one current, this is another current, this is third current, this is fourth current, right? So we should have 4 values. So let us see. First one is moving in the outward direction, but we have current in the opposite direction, so it will be -2 because the current value is already given, so we do not have to write down any voltage or ratio. Then next one will be plus V1 divided by 5, right? Then next one will be plus V1. This is moving with this 330 I1. This source is a current dependent voltage source, so we have to consider this as a voltage source, right? So the value of this voltage source is 30 I1, and it is moving from negative to positive, so it will be plus. So it will be 30 plus 30 I1 divided by the resistance, which is 10. Then last one is V1 minus 50, right, divided by, now here as we can see we have two resistances, so it will be addition of both the resistances, so it will be 20 plus 10 equals to 0. Okay, so now here we have one equation and two unknown. This is another unknown which is coming from the dependent source. So what is the value of this current I1? So as we can see from the circuit itself, this is our current I1 moving in this direction, right? So what is current I1? So I1 is nothing but, with respect to the branch, it will be V1 minus 50 divided by 20 plus 10 is your 30, right? So this is our I1. So we are going to place this value of I1 here in this equation. Okay, so after putting the value here and solving, what we get is V1 value will be equals to 20 volt. Okay, so it is as simple as that. So now like this we can solve numericals containing dependent source, and we can use it or determine it using our nodal analysis. Okay, so this is all about nodal analysis. So I hope you have understood how it can be done, plus what are the rules and regulations for solving any circuit using nodal analysis, plus we can also apply it in using dependent sources. So do try this type of questions, and I hope it will be beneficial for you. Thank you for joining, and we'll meet soon for our next discussion. Thank you.